Welcome to EPG Pathshala. This module deals with environmental aqueous solutions of gases, acids, bases and pH. Environmental chemistry, we deal with soil, water and gases. Aqueous solutions are usually dilute solutions and they are cause of contamination by several contaminants. Their concentrations being small, they are expressed in terms of molarity and some other units. In this unit, we will discuss the dissolution of gases, acids and bases in aqueous solutions, dissociation of weak acids and dissociation of weak bases, strong acid, strong bases. Another most important point is the pH. pH is the measure of hydrogen ion concentration in aqueous solution. So, we will also discuss it in this module. Solution is a homogeneous mixture of two or more substances. It can be made by mixing substances in any physical state. Solution of a gas in gas, solid in solid, that is known as solid solution, liquid in a liquid, solid in a liquid and gas in a liquid. The substance which is present in large amount is called solvent and the other present in small amount is called a solute. This is particularly applicable in case of solutions in water which will be concerned in environmental chemistry. Solution of NaCl in water. NaCl is the solute and water is the solvent because solute is present in small amount and solvent is present in large excess. Solutions in environment, there are mostly dilute aqueous solution. Remember, the thermodynamic criteria of dilution is heat of mixing must be equal to 0, volume of mixing equal to 0 means there should be no heat change and there should be no volume change when solute is mixed with the solvent. What is this definition of the solubility? The maximum amount of substance per unit volume of the solution that is soluble in a solvent at a given temperature is known as solubility of the substance at that temperature. It is important to remember that the solubility changes with temperature. Therefore, specifying temperature is important. A solution can be saturated, that is whatever amount was soluble has been dissolved in the solution. If this amount present is less than the solubility, we call it a unsaturated solution. If the amount present is amount dissolved is more than the solubility, we call it a supersaturated solution. The concentration of solute can be expressed in several ways. One of them is concentration of solute in mass percent, W by W or M by M. Mass percent of the solute, mass of the volatile, mass of the solute into 100 divided by total mass of the solution. Concentration of solute mass by volume. Here, the mass of the solute is taken in mass unit and the solution is taken in volume unit. The solute concentration mass by volume is given by mass of solute in gram into 100 divided by volume of the solution milliliter. Concentration of solute volume by both are in the volume unit. The solute concentration volume percent equal to volume of the solute into 100 divided by total volume of the solution. Take example, a problem for example, what is the concentration of NaCl in mass percentage? If 5 gram NaCl is dissolved in 75 gram water, I may point out here, at many places instead of W by W you will find M and M, both are one and the same thing and they are interchangeably used. From equation 1, you can find mass percentage of NaCl equal to the amount of NaCl dissolved into 100 divided by total mass of the solution, that is solute plus solvent, which comes to be 6.25%. If 4 gram CaCl2 is dissolved in water and solution is up to 50 milliliter, that is this is the volume and this is the mass dissolved. Calculate the concentration of CaCl2 in mass by volume percentage equal to this, the amount of the solute into 100 divided by volume in milliliter. So, the unit of this will be gram per milliliter. Another example, if 2.2 milliliter alcohol is mixed with water and the solution made up to 50 milliliter, remember the solute is in milliliter, the solution is also milliliter, both in the same unit. Calculate the percentage, it comes to 2.2 milliliter into 100 divided by volume of the solution. So, this is 4.4%, this is volume by volume. Now, this is very important. Solution of gases in water, that is described by Henry's law. The gases dissolve in water. For example, oxygen dissolves in water and dissolution of oxygen is what is very necessary. It is governed by Henry's law. If we have a substance X, this, and this dissolves in water, so there will be equilibrium between gaseous molecules in the gas phase and molecules dissolved in aqueous solution. Okay, this is sort of chemical equilibrium. So the chemical equilibrium for this is known as Henry's constant Kh equal to the concentration of gas dissolved in water divided by partial pressure of the gas. Remember, there are two different units. This is mole per liter and this is in atmosphere, or it can be in other unit also. The value of K is temperature dependent. This depends upon the temperature. Also depends on the nature of the gas and nature of the solvent. It is not necessary that all gases in water or any other solvent will have same solubility, they will differ. Another thing, nature of the solvent. Some solvents are polar, some solvents are non-polar. On this factor also the solubility will depend. KH is also dependent on temperature. In general, the solubility of the gases in aqueous solutions or in solutions decrease on increasing temperature in general. Now, these are the values of Henry's law constant for different gaseous forms. This is the temperature dependence of the gas, as I told you. Dissolution of O2 in water. Now, this dissolution of O2 from ecological point of view is very important for aquatic species, because if oxygen is not there, the species will not survive, because to sustain life, they need oxygen. So, a proper amount, an optimum amount of oxygen must be there, and this is governed by this law, Henry's law. This KH equal to O2 in the aqueous phase divided by partial pressure of oxygen, and at 25 degree Celsius, Henry's law constant has this value. Corresponding to partial pressure of 0.21 in dry air, the solubility of O2 at this temperature is calculated to be this, mole per liter. This can be converted into gram also, based on molecular weight of 32 gram per mole of solubility of oxygen in milligram per liter is this, and milligram per liter is equal to ppm, 8.7 ppm. So, in water you can expect at room temperature of 25 degrees Celsius the solubility to be 8.7 ppm or 8.7 milligram per liter. With decrease in temperature, solubility increases and becomes 14.7 ppm at 0 degrees Celsius. Now, what is the reason for this? Actually, as the temperature increases, the kinetic energy of the gas molecules increase and they escape out. Therefore, with the increase in temperature, the solubility decreases. Now, if there is a river and the temperature of the river body or a lake or any water body increases, then what will happen? As per this law, the solubility will decrease and oxygen will be less. What will happen? The aquatic species present in water will have less oxygen for survival. So, they will start dying. This happens when there is thermal power plants or other factories release hot water in the river bodies. Dissolution of SO2 in water. This is very important. SO2 is cause of acid rain. It is sulfur dioxide. We will discuss later on about it. It is a key trace atmospheric gas responsible for acid rain. It gets dissolved in cloud water or in falling raindrops. Remember, sulfur dioxide is present in gas molecules in atmosphere. When it rains, the drops come out. There is a collision between the SO2 molecules and the raindrop, and in raindrop, SO2 molecules dissolve. And this dissolution is expressed by this Henry's law. SO2, H2O, KH, and remember this chemical species is formed SO2 dot H2O. This is also written as H2SO3 or sulfurous acid. This SO2 H2O, there are three equilibria, at least three equilibria. This SO2 H2O is a weak acid, it dissociates to give you bisulfite ion, hydrogen ion. This may further dissociate to give you sulfite ion and hydrogen ion. So, solubility of SO2 in water will be governed by these three equilibria. Another thing, there is hydrogen ions are there, so the solubility will be pH dependent. KH is defined by this equation, by mass, but the total SO2. In SO2, the oxidation state of sulfur is 4, base 4. That's why it is also written as sulfur 4. Sulfur 4 includes all SO2 species in which the oxidation number of sulfur is 4. So, the total SO2 that is dissolved in water, that is SO4, S4 equal to this, SO2 dot H2O, Y-sulfitine and sulfitine. From this equation, K equal to this into this upon this. Therefore, HSO3 equal to, will be equal to, we can calculate by this equation SO here. So, this equal to this. Similarly, from the previous equilibrium, you can see sulfitine concentration equal to this, where remember K1 and K2 are the first and second dissociation constant. By substituting these values here, you can get this equation on rearrangement. And remember, this is pH dependent. K1 has a value of this, K2 has a value of this. Now, what happens? Look here. This is K1, K2 upon H plus square. As the hydrogen ion concentration will increase, the solubility of sulfur 4 will decrease, SO2 will decrease. And if the pH increases, the solubility of sulfur dioxide in water will increase. In India, the rainwater pH is high. In European countries, rainwater pH is low. Therefore, sulfur dioxide will be more soluble in rainwater or cloud water in our country than in European countries. It may be pointed out that increase in pH from 1 to 8 increase the concentration of dissolved SO2 in water by a factor of 10 to the power 7 times. Dissolution of ammonia. Ammonia is another trace atmospheric gases. Gas, it is a pollutant, and its salts, ammonium sulfate and ammonium nitrate, are present as aerosols. Ammonia is formed in the atmosphere from agricultural activities and also for anaerobic degradation of nitrogen compounds. In India, ammonia is reported to be in the range this 7 to 56 microgram per meter cube. Its dissolution equilibrium is this. This Henry's law, NH3 dissolves in water and this form NH3 dot H2O, or this is also written as NH4OH. This is gas and this is liquid. And this dissociates to give you well-known ammonium ion plus OH ion. So, solution of ammonia in water is alkaline because of the production of OH ions. The formation of hydroxide makes solution alkaline and the pH of the solution increases. The total dissolved ammonia concentration, whereas 3T in water, it can be shown as in case of SO2, that is this NH3 T equal to this equation. This PNH3 is the partial pressure of ammonia in atmosphere, this is OH ion concentration, and this is Henry's law constant. Dissolution of strong acids, HCl, HNO3, etc. Trace amounts of HCl, HNO3 and other strong acids are found in atmosphere. Remember, they are present only in small amounts. These, on dissolution, they fully dissociate in water. For example, HNO3 will dissolve in water to form hydrogen ions and nitrate ions. If we apply Henry's law to it, we will get it KH equal to this into this divided by the partial pressure of HNO3, this. KH is very high, the dissociation of these acids in dissolution is complete. So, you can say, since whole of HNO3 has dissociated, so what will happen? Whatever HNO3 was present in gas phase, now it is converted to hydrogen ion and into nitrate ion. So, you can say they are equal to this. And equation 19. From this you can find dissolved HNO3 equal to KH into PHNO3 square. This equal to this. Dissolved HNO3 equal to H plus equal to this equal to nitrate plus, because it dissociates 100%. So, instead of H plus we can write here HNO3. In place of nitrate we can write HNO3. This becomes HNO3 square. So, KH equal to HNO3 square upon PNH3. So, or KH into PHNO3 equal to HNO3 square. Therefore, dissolved HNO3 equal to square root of all this. So, for concentration of dissolved HNO3, this is dissociation of water. Water is very weak electrolyte. It dissociates to a small extent, but it does dissociate and give hydrogen ion and OH ions. The equilibrium constant for this is this into this upon H2O. I will tell you, in chemistry books, it may be written differently. It may be written H2O plus H2O equal to H3O plus OH, but it makes little difference. We write it this way or the other way. Okay? Water dissociation is very expensive. So, this can be taken as constant because its dissociation is very small. It is around 55.5. Very small, so it can be taken as constant. Then we can write Kw equal to H into H. So this is known as ionic product of water. In aqueous solution, hydrogen concentration is 10 to the power minus 7. Hydroxide concentration also 10 to the power minus 7. If we substitute it here, we get Kw is equal to 1 into 10 to the power minus 14. If we take log of this, we will get log Kw equal to log H, log OH, and if we minus put here a Kw equal to 10 to the power minus 14, this will be minus 14 equal to log H plus log OH. Minus 14 equal to minus log H minus log OH. Writing minus log H equal to pH and minus OH equal to pOH, because it becomes pH plus pOH equal to 14. In pure water, they are equal to this. pH of aqueous solutions. Now, how hydrogen concentration is expressed? For example, we have a water sample. It must be having some hydrogen. If we measure its hydrogen and write it in the form of pH, then this will be the expression. pH equal to minus log of log hydrogen concentration. Take the log of hydrogen concentration, put a minus sign before it, and what is the value? That is the pH. Concept of pH is used only in aqueous solutions, and particularly those are dilute. If we have a 10 m H2SO4 solution or 5 m HCl solution, then the concept of pH is no more valid and should not be used. It is used only in dilute solutions. In environmental chemistry, solutions mostly encountered have pH in the range 3 to 10. pH is very useful in expressing the acidity of groundwater, rainwater, fog water, sea water, and of all other water bodies. The way we express hydrogen concentration, we can also express OH ion concentration. A similar definition, pOH equal to minus log OH. Now, we can take an example to express the point. Calculate the pH of a 2 into 10 to the power minus 4 mole per liter aqueous solution of HNO3. It must be pointed out that the hydrogen concentration must be in this unit if you want to calculate the pH, mole per liter. If it is any other unit, convert into this. pH of a 2 into 10 to the power minus 4 solution of HNO3. HNO3 is strong acid. It will fully dissociate. So what will happen? 1 HNO3 gives 1 hydrogen. It means 2 into 10 to the power minus 4 mole per liter HNO3 will give 2 into 10 to the power minus 4 mole per liter hydrogens. So pH equal to, by definition, minus log of this. We solve it and get an answer of 3.7. Just see, minus log 2 plus log 10 to the power minus 4, or log 10 to the power minus 4 equal to minus log 4. This is 0.30. This is 3.7, minus 3.7, minus, this becomes 3.7. pH always have a positive sign. Calculate the pH of a 2 into 10 to the power minus 4 mole per liter aqueous solution of LOH. Remember, that was H ion, this is OH ion. OH is a strong base. It will fully dissociate. 2 into 10 to the power minus 4 mole per liter of LOH will give you 2 into 10 to the power minus 4 mole per liter of OH ions. What is pOH? Look here, minus log 2 into 10 to the power minus 4, just solve it, you will get 3.7. You want pH? Remember this formula, pH plus pH equal to 14, pH equal to 14 minus 3.7, so you get pH equal to 10.3. So you must remember, in alkaline solutions, the pH is more than 7. In acid solutions, the pH is less than 7. Solutions of strong acids and strong bases. In aqueous solutions, strong acids such as HCl, HNO3, H2SO4, HBr, and strong bases such as NaOH, KOH are all strong electrolytes and hence fully dissociate. So you can take them fully dissociated, and their concentration will give equal amount of hydrogens and the anions. Solubility product, this is again important concept, because many solutes dissolve in aqueous media, they precipitate out, and that is governed by the equilibrium, solubility equilibrium. Suppose we have a salt Va, it dissolves, the salt is present as B plus and A negative. The solubility product is written like this. B aqueous, this is taken as constant, because this is solid. Pure solid and pure liquid, their activity is taken as unity or constant. So, solubility product is this. The solubility product is also written in the P form, pK form. pK is equal to minus log of equilibrium constant of the solubility product. The solubility of hydroxide is pH dependent. They are hydroxides. How? At higher pH, solubility shall be low. For example, if we take iron, this iron. Iron in a 0.1 m solution, it is presented as iron 3 plus. If we increase pH, what will happen? Iron will precipitate out as hydroxide. So, in solution, the iron concentration will decrease and it will precipitate out in the form of hydroxides. So, in such cases, the solubility decreases on increasing pH and less amount of ions are present in solution. This is true of this also, this is true of this also, true of this also. pH of solutions of weak acid, weak bases, this is important. There are some important acids are formic acid, acetic acid, hydrogen cyanide, ammonium hydroxide, H2S. They are environmentally important. The dissociation of an acid can be written as HA equal to H plus plus A negative. Suppose you have taken initial concentration is A and alpha is the degree of dissociation, then the amount dissociated will be A into alpha. So, if you started at A, initial concentration is A, then at equilibrium it will be A minus A alpha. This will be A alpha, this will be also be A alpha. At equilibrium, if equilibrium constant, K equal to this into this upon this, writing their concentration you can write. Remember, like pH, we can also write pKa. pK means negative log of dissociation constant. Likewise, in case of bases, we can write pKb, that is minus log of dissociation constant of a base. In this equation, Ka equal to H plus into HA, negative HA. If we substitute these values, this become A alpha into A alpha upon A into A minus A alpha. A alpha, since they are weak, their dissociation is very small, so A alpha will be negligible as compared to A. We will get A alpha into A alpha upon A, or ultimately by modification or simplifying, we will get K equal to A alpha square. That is so real. This we will get, and alpha equal to square root of this. In case of base, instead of K, we will have this. Lowering of vapor pressure of solutions. This is again an important concept. What will happen? If you take water, put it in a beaker, allow it for some time, over the surface of liquid water, there will be water vapors. And the partial pressure of water vapors will be fixed. But what happens if you add a sodium chloride to water and close the vessel and then measure the partial pressure? The partial pressure will be less now, because the addition of non-volatile solute has decreased the vapor pressure. Now, these two things are very important in deciding the freezing points and boiling points of the substances. This is also important here. The water soluble aerosols particles lower the value of the supersaturation required for the particles to serve as cloud condensation nuclei. This aspect is helpful in inducing rainfall and also in artificial rainfall. So, this concept is important in environmental chemistry and in meteorology. In this presentation, an attempt was made to explain the solubility of gases, liquids and solids in solutions, particularly aqueous solutions, how their concentrations are expressed in mass by mass, in volume by volume or mass by volume units. These solutions are very important because trace amount of substances are present in water which are toxic, and their concentrations must be explained in that way. The solubility of the gases has been explained to you. This is governed by Henry's law. For example, the pollutant sulfur dioxide, the life savior oxygen dissolves in water, they are also important. Then the solubility product, how the solubility is governed by equilibrium, how the weak acids and weak bases dissolve. The most important concept of pH was explained to you, how pH is expressed and what are by giving you some numerical examples. Thank you.